The goal of this video is to explain how Bitcoin works under the hood, to give a clearer idea of what it really means to own, send, or mine Bitcoins. First, a brief high-level overview of what Bitcoin is. At its core, Bitcoin is just a digital file that lists accounts and money like a ledger. A copy of this file is maintained on every computer in the Bitcoin network. These numbers don't represent anything in the physical world. They only have value because people are willing to trade real goods and services for a higher number next to their account and believe others will do the same. The numbers only have value because we believe they have value, just like any other fiat currency. To send money, you broadcast to the network that the amount on your account should go down and the amount on a receiver's account up. Nodes or computers in the Bitcoin network apply that transaction to their copy of the ledger and then pass on the transaction to other nodes. This, with some math-based security, is really all there is, a system that lets a group of computers maintain a ledger. While this may sound similar to the way a bank maintains a ledger, the fact that the ledger is maintained by a group rather than a single entity introduces a number of important differences. For one, unlike a bank where you only know about your own transactions, in Bitcoin everyone knows about everyone else's transactions. Also, while you can trust your bank, or you can at least sue it if something goes wrong, in Bitcoin you're dealing with anonymous strangers, so you shouldn't trust anyone. The Bitcoin system is amazingly designed so that no trust is needed. Special mathematical functions protect every aspect of the system. The rest of this video will explain in detail how Bitcoin allows such a group of strangers to manage each other's financial transactions. At a basic level, for Alice to send money to Bob, she simply broadcasts a message with the accounts and the amount. Send 5 Bitcoins from Alice to Bob. Every node that receives it will update their copy of the ledger and then pass along the transaction message. But how can nodes be sure that the request is authentic, that only the rightful owner has sent the message? Bitcoin rules require a kind of password to unlock and spend funds, and this password is what's called a digital signature. Like a real handwritten signature, it proves the authenticity of a message, but it does so through a mathematical algorithm that prevents copying or forgery in the digital realm. Unlike a simple static password, a completely different digital signature is required for every transaction. Keep in mind that in Bitcoin, you're dealing with complete strangers, so you never want to reveal a password that could be copied and reused by someone else. A digital signature works by utilizing 2 different but connected keys, a private key to create a signature and a public key that others can use to check it. You can think of the private key as the true password and the signature as an intermediary that proves you have the password without requiring you to reveal it. Public keys are actually the send to addresses in Bitcoin, so when you send someone money, you're really sending it to their public key. To spend money, you must prove that you're the true owner of a public key address where money was sent, and you do that by generating a digital signature from a transaction message and your private key. Other nodes in the network can use that signature in a different function to verify that it corresponds with your public key. Through the math behind the digital signature, they are able to verify that the sender owned a private key without actually seeing the private key. Importantly, because the signature depends on the message, it will be different for every transaction and therefore can't be reused by someone for a different transaction. This dependence on the message also means that no one can modify the message while passing it along the network, as any changes to the message would invalidate the signature. The math behind this is fairly complex, and while I won't try to explain it fully now, here are some topics you can Google to get started: elliptic curve digital signature algorithm and mathematical trapdoor. More at the end of the video. So far, we know that digital signatures are used to ensure a transaction is authorized, but I've oversimplified how nodes in the network keep track of account balances. In fact, no records of account balances are kept at all. If you don't keep track of how much money any given person has, how do you know if they have enough to send to someone else? Instead of balances, ownership of funds is verified through links to previous transactions. Here's how this works. To send 5 Bitcoins to Bob, Alice must reference other transactions where she received 5 or more Bitcoins. These reference transactions are called inputs. Other nodes verifying this transaction will check those inputs to make sure Alice was in fact the recipient, and also that the inputs add up to 5 or more Bitcoins. Let's look at a real transaction to see this in practice. This transaction references 6 inputs for a total of 139.6 Bitcoins. In the output section, notice that there are 2 lines. The first one of these is actually going back to the sender as change for the transaction. A simplifying rule states that each input must be used up completely in a transaction. So if you're trying to send an amount that doesn't exactly match one of your inputs, you need to send any remaining amount back to yourself. Through these reference input linkages, ownership of Bitcoins is passed along in a kind of chain, where the validity of each transaction is dependent on previous transactions. But how can you trust those previous transactions? You can't, and you should check their inputs too. In fact, when you first install Bitcoin wallet software, it downloads every transaction ever made and checks each one's validity all the way back to the very first transaction. Remember, you're dealing with complete strangers, so it's important to verify every transaction for yourself. This process can take over 24 hours, but it only needs to be done once. Once a transaction has been used once, it is considered spent and cannot be used again. Otherwise, someone could double spend an input by referencing it in multiple transactions. When verifying a transaction, in addition to the other checks, nodes also make sure that inputs haven't already been spent. To be explicit, for each input, nodes check every other transaction ever made to make sure that input hasn't already been used before. While this may seem time-consuming as there are now over 20 million transactions, it's made fast with an index of unspent transactions. So instead of a ledger of balances, Bitcoin nodes keep track of a giant list of transactions. Owning Bitcoins means that there are transactions in this list that point to your name and haven't been spent, or in other words, used as inputs in other transactions. One interesting consequence of this ownership structure is that figuring out your own balance requires iterating through every transaction ever made and adding up all your unspent inputs. Another interesting note about transactions is that the system can support more complex ones than simply sending funds to one person. You may have noticed a cryptic-looking line of text in the output shown previously. It turns out that outputs are more like puzzles to be solved rather than simple to addresses. Rather than emailing, sending money in Bitcoin is more like putting money in a public locker and attaching a math puzzle that must be solved to open it. The puzzle is defined using a special scripting language, and while it's typically designed so that only a single owner of a public key can solve it, more complex conditions are possible. For instance, 2 out of 3 signatures could be required for an escrow-based transaction. Another example is the very first Bitcoin transaction ever made, which was a puzzle that anyone could solve. While most Bitcoin software hides the scripting layer for you, you're free to write your own software and claim conditions, although this can be risky. Over 2,600 Bitcoins were lost in one batch of transactions due to a malformed address. This highlights an important part of Bitcoin. As there is no bank or credit card company you can appeal to, any user error mistakes can result in permanent loss of Bitcoins, and not just from your own account, but from the Bitcoin economy overall. If you lose your private key, any funds associated with the corresponding public key will be gone forever. Because people will likely lose private keys due to hard drive crashes and insufficient backups, this means the Bitcoin currency will eventually be a deflationary one. Before explaining the final piece that secures Bitcoin, mining, I want to highlight a few points about anonymity in Bitcoin. If you access Bitcoin through a Tor network that hides your IP address, you can use Bitcoin without ever revealing anything more than your public key. And to avoid someone linking your transactions together, remember they're all publicly stored on every computer, you can generate a new public key for every incoming transaction. It is possible, however, to inadvertently link public keys together. In the transactions shown earlier, 6 input transactions were used as sources, and despite the fact that all those inputs were sent to different addresses, they all became linked in that transaction. The sender proved that he owned all of those addresses by supplying the digital signature to unlock each one. Researchers have in fact used these links to study Bitcoin user behavior. You might think that generating a public key receiving address could potentially create a link to your true identity, but even this step is anonymous and amazingly can be done with no connection to the network. You simply click a button in your wallet software and it randomly generates a new private and public key. Because there are so many different possible addresses, there's no reason to even check if someone else already has that key. Compare this to signing up for an email address where almost everything you might try has been taken. In fact, if you did guess someone else's key, you would have access to all their money. This is the total number of possible Bitcoin addresses. These large numbers protect the Bitcoin system in several ways, so it's useful to try to appreciate just how big they are. Some estimates for the number of grains of sand in the entire world are around 7.5 million trillion. Now imagine that every grain of sand represented an entire other Earth of additional grains, and you're still much smaller than the possible number of Bitcoin addresses. Let's recap Bitcoin security so far. By verifying the digital signature, we know that only the true owner could have created the transaction message. And to make sure the sender actually has money to spend, we also check each referenced input, making sure it is unspent. But there is still one large security hole in the system that can make this unspent check unreliable, and this has to do with the order of transactions. Considering that transactions are passed node by node through the network, there's no guarantee that the order in which you receive them represents the order in which they were created. And you shouldn't trust a timestamp because someone could easily lie about the time a transaction was created. Therefore, you have no way to tell whether one transaction came before another, and this opens up the potential for fraud. A malicious user, Alice, could send a transaction giving money to Bob, wait for Bob to ship a product, and then send another transaction referencing that same input back to herself. Because of differences in propagation times, some nodes on the network would receive the second double spending transaction before the one to Bob. And when Bob's transaction arrived, they would consider it invalid because it's trying to reuse an input. So Bob would be out both his shipped product and his money. Overall, there would be disagreement across the network about whether Bob or Alice had the money because there's no way to prove which transaction came first. In light of this, there needs to be a way for the entire network to agree about the order of transactions, which is very much a daunting challenge in a decentralized system. Bitcoin's solution is a clever way to both determine and safeguard the ordering through a kind of mathematical race. The Bitcoin system orders transactions by placing them in groups called blocks and linking those blocks together in something called the blockchain. Note that this is different from the transaction chain we discussed earlier. The blockchain is used to order transactions, whereas the transaction chain keeps track of how ownership changes. Each block has a reference to the previous block, and this is what places one block after another in time.